So we've been using blue waters to study variations in the explosions of massive stars. We have a fairly large group. I've highlighted in blue those members who've been involved in running data analysis and or simulations on blue waters. This has been supported by 2 PRAC projects for almost 5 years now. So why are we interested in supernovae and how stars explode? Well, we want to understand which stars explode, why they explode. It's an important phase in the life cycle of stars. The observers have lots and lots of data to compare to. We do okay with what little comparison we've been doing. There's a lot of exotic physics to look at, nuclear physics. We have neutrinos. We have a little bit of GR, not nearly as much as some of the other things you've seen here today, and including multi-messenger signals, which we are also working on processing. And our group is particularly interested in the generation of new elements and how they get enhance the formation of the next generation of stars. So the basic paradigm of the core collapse supernova is a massive star forms an iron core at the center. It becomes unable to hold itself up and collapses. It collapses until its density reaches the density of an atomic nucleus, and then it stiffens and a shock forms working its way out. This shock is pushing against the infalling material, and you have a balance behind the shock between the thermal and turbulent pressures on the inside and the ram pressure of the accretion on the outside. This cavity is being heated by neutrino emission that drives convective flows. And so this involves a lot of various inputs and ingredients to the problem. I mentioned the neutrinos, so we have to deal with the neutrino opacities, neutrino transport. We have the nuclear matter I mentioned, and there's nuclear reactions in the nuclear networks on the outside, and this is particularly important if we want to capture the element formation. And then, of course, because it's a hydrodynamic problem, we have all of the issues associated with resolution and dimensionality of our fluid dynamics. So our code is called Chimera. It's one of the codes that has all of those pieces put in. I won't go over the details. I'll note that we have a paper describing our code at great length, and we also include passive tracer particles so that we can do even more post-processing of the nucleosynthesis. This slide sort of summarizes all of the runs we've been doing for the last, decade. And I want to focus primarily on the stuff we've been doing on blue waters, but I'll do a little bit of preview. We organized them into these lettered series to sort of symbolize the combination of choices of physics, numerical methods, and that, of course, and implementation, which, of course, includes any flaws. So our first sort of result in our pre-blue waters days were to run models for a fairly long time, about 1 second each. That doesn't seem like long to most of us, but in core collapse, that was a long time. And we were able to match reasonably well, though a little bit on the low side, with our black dots to the observed colored crosses of the observers. And we've recently redone this with the same version of the code and basic physics in all of our blue water simulations, though again, this wasn't done on blue waters. And we get very similar answers with the stars. And you can see we're now running for 2 or 3 seconds for each of our models until they reach the helium shell. The last sort of major accomplishment before blue waters was our first 3D run. It was one of the first handful of 3D simulations that would explode with all the physics. And it develops this large plume and this axis of dimension, this axis with the big plume on one side and accretion on the other. Among the first things we did with blue waters was to repeat this explosion at 2 lower resolutions, and each of those, as we dropped the resolution, it became less explodable, less vigorous in its explosion. It took longer for it to happen. And I'm currently moving all of the data related to those 2 additional models and running the analysis on them, and hopefully we'll have a paper finished this summer. So in addition to the 3D stuff, which will be the primary focus, I want to mention 2 groups of 2D models that we've been running. This is a large set of models with the primordial composition covering a wide range in masses. And this plot traces the growth of the explosion energy over the course of about 2 seconds. The typical sort of textbook answer for how explosive, how energetic is a supernova is about 1 beta, or 10 to the 51 ergs. But we know that some are weaker and some are stronger, and we're getting a wide range here. The most energetic of these have the most massive protoneutron stars, and it correlates pretty strongly. And you can look at that with the plot. And it seems that somehow that makes the engine more efficient. I have a few ideas. I certainly don't have time to share them with you. But primarily, I'd like to talk about our 3 most complete 3D models. These are all 1-degree resolution models computed with a yin-yang grid. These were all done completely. These were all done on blue waters. And they represent 3 different structures of stellar progenitors. And I think they make a good comparison set because of that. So in green, we have a 9.6 solar mass star. This is a very low mass iron core with a very low density envelope outside. This star will actually explode in 1D, but not very strongly. The black line is our medium star. It's got a sort of medium iron core, and it grows. So this is the one you saw just a moment ago in motion. And then the 25 in red is the second most energetic of those 2D models from that set, and it seems to be kind of enthusiastic. Is it? Well, and here we can see the growth of the neutron stars, and they correspond to those iron core masses, just as we said a moment ago. And on the right, we have the growth of the explosion energy. And the explosion energy of the lightest core grows quickly and then saturates, and you can see that it just sort of flatlines, and that's because it runs out of stuff to heat. The 15 with the medium-sized neutron star takes a little while to get going, and then has a nice bit of growth there at the end. It's still presumably has a ways to go, but it probably will not make it there. Not enough computing time. The 25, which was the enthusiastic one from the 2D, is likewise enthusiastic here. Its massive neutron star is again giving it quite a strong explosion. It's almost as strong as some of those 2D models from the very first set, very quickly and in 3D, so this is nice. If we look at, so the explosions are driven by neutrino heating, so we can look at the neutrino luminosity, and if we ignore the little burst at the beginning, we see the period after that. The hierarchy of neutrino luminosities corresponds to the hierarchy of neutron star masses. And on the right, we have the total heating in that region between the neutron star and the shock, and the green one that has very weak heating, and it just drops off really fast. The black one is the 15 that we've done this one before. It looks very much like the 15 version that we did before Blue Waters, so that's reassuring, very similar. And then the very energetic 25 has a very strong heating rate, and it's dropped down actually below the 15 at this time, and so I'd really like to know what happens next, but some other supercomputer might have to help us with that. Here we can see those 2 models in motion, a little slice through the 15 on the left, and we can see its various plumes, and as the shock expands, it organizes it so that there's one primary plume on the lower right, and there's an accretion on the opposite end in the upper left. And then the 25, which was our very energetic model, seems to organize itself into a big plume even faster, and again, there's an opposing accretion stream. These are frames about every 20 milliseconds, because I'm not very good at volume rendering. So a quick look at the third of the 3 models. We did that low mass 9.6 star with a large nuclear network in the simulation, so we're able to look at some exotic nuclei, if you like. And because that explodes so rapidly, the outer bits of the ejecta are still very neutron-rich, and so we get neutron-rich isotopes like calcium-48, which is, I think, about 1 or 2% of all the calcium here on Earth. And among the things that we're doing in taking these products of our work on blue waters and using them for other things is to continue those explosions without the neutrinos driving them into the rest of the star and disrupting it. And this is some work on the left that has been done at Oak Ridge using our blue waters generated data. as an initial data point, and it shows the shock after it propagates outward. Here's a few abundance contours of a handful of isotopes, and you can see these little mushroom-like plumes sticking out of some of the ejecta that came from deep inside. They're draped in helium from the helium shell and poking deep into the hydrogen-rich layer, and the outer surface of the shock is basically at the tips of those features. It took it about 80,000 seconds for it to poke through to the surface, and this is some work that one of our graduate students has been doing essentially outside of the main Chimera project, so using our data. Another of our students, I think about 2 or 3 years ago, started a series of runs on blue waters looking at the effect of the nuclear equation of state. It's one of the critical inputs that comes from outside, and we've been using the equation of state that's represented by the line that's different than the others. That's an equation of state from the early 90s, and there have been a lot of work in the nuclear physics community developing new equations of state based on constraints from nuclear physics and from observations of neutron stars and the like. And while they're not all identical, they are sort of clustered together, and this is interesting. And Ryan finished his PhD and wrote his dissertation on this, and he's working on a paper from this. And a lot of our community is moving on to one of those in the cluster there. I can't remember which one it is, color-wise. And we will in the future as well. So our work is informing some of the ways that we're making choices about what we do next on blue waters or elsewhere. So with blue waters, we've generated a lot of simulation data. And we're working on analyzing it. And there's a lot of interesting behavior and phenomena. And we've found some of it. We know there's a lot more to find. I've showed you just a little bit of it. And we've been able to use blue waters to examine the differences in structures of stars and see how that impacts the way the explosions happen, and to understand some of these things like the nuclear equation of state and resolution effects from the earliest work. And then all of this is being tossed into analyses for things like neutrino signals for neutrino detection, gravitational wave signals, and post-processing of all of those particles so that we can develop the ejecta nucleosynthesis. And so we're continuing on with our program, and we look forward, and I thank you for your time.